Chlorate. Is there a chlorite? Okay, nitrate. Is there a nitrate? Yes, nitrate then would be NO3 because the 8s are more than the ites. Chromate.
That's a no.
Chromium and oxygen. And dichromate. And when you memorize this, you might have said dichromate. You just take that and double it to make 2 of them. But it's 1 less than 2 of them. See, 2 chromiums, but only 7 oxygens. So dichromate is Cr2O7. But notice the charges are still both -2 or 2 negative. So you can't go by the numbers to figure out what the charge is going to be. You just need to memorize the formulas and memorize the charges. And phosphate is PO4, 3 negative. All right, so I'd probably give you just, hopefully you marked where they're wrong, but I would probably give you, I would consider the formula and the charges as 2 separate things. So if you got the formula right and you got the charge wrong, you get half credit. So formulas and charges are what I'm going to be looking at. So when you're done marking those up, maybe tell the other person if they care to know what they've received. And then pass them back to Derek. Derek, if you just set them on the desk right there on the side. So we can get into the fun stuff, okay? Now that the quiz is over, let's move on into VSEPR theory.
I love Vespers.
VSEPR. Now, for those of you that can read English letters, you're going to realize that VSEPR, it's pronounced Vesper, but it doesn't spell Vesper, does it? But it's easier to say Vesper than it is to say VSEPR. VSEPR. So VSEPR is the way you remember it. So you remember it as Vesper, you pronounce it as Vesper, but it's actually an acronym taking the first letters of valence shell electron pair repulsion, VSEPR. Okay? There's lots of different ways to teach this stuff, and frankly, I didn't review the way I've taught it in years past, so hopefully this will be a combination of what I remember, plus maybe a few fresh new things this year. Maybe not. Maybe I'll watch last year's and the year before video and find out, you know what, I did it the same boring, bad way then too. But we'll learn together, figure out how it comes out this year. Now, so valence shell electron pair repulsion. Take just a minute, think of those words. What is the basic concepts we're talking about then? We're looking at what electrons? Those that are in the valence, right? The valence shell electrons. Electrons, remember, are negatively charged. We're talking about geometries now. And so in geometries, what we're trying to compute or figure out is where do we find an equilibrium place? Well, hopefully you recognize that electrons, because they're all negative, that they repel one another, right? And so part of what we're going to learn is the symmetry of the molecules and how the bonds and the pairs lay out in the molecules is based upon this repulsion between electrons, but not simply electrons, but electron pairs. Electron pairs. Now we did the Lewis structure, and some are single dots and some are double dots. And some of those are bonds and some of those aren't bonds. We're going to be looking at how those lay out in a 2-dimensional Lewis structure and then visualize that and move it forward into a more appropriate, a more accurate 3-dimensional space. And that's what VSEPR is all about. It kind of reminds us back when we talked about Democritus and Plato, and they talked about continuous and discontinuous theories of matter, and how the ancients thought of matter as, every different kind of element had a different kind of a shape. And we kind of scoff at that. No, come on, all atoms, they look exactly the same. They got a nucleus, they've got electrons now. We're more sophisticated than that. When we get into molecules, we're going to actually find out that molecules have distinctive geometries. In other words, if you could look at the molecule based upon how it's built, what its components are, or more specifically, how it's bonded together, it would actually have a particular shape. Not everyone is unique, but there's a handful that we're going to discuss. There are a lot more geometries than we're going to cover. Okay, but we're going to cover 5 dominant ones that you need to understand. And I'm already about 3 pages behind on my notes. So let me flip forward to where we are at least and try to stick with the notes. What I'm going to do with each one of these 5 types, or these 5 geometries, is give you a bond angle the name and the bond angle, and then use some slides to describe it, and then go over there and pull one of my models from last year to show you what it looks like. Okay? And what we're going to be doing primarily is considering what would this molecule look like in two-dimensional space, and then how does that convert into three-dimensional space. We said before, two-dimensional space is a way of understanding it, but it's not really fully accurate. Just like your shadow, I might be able to look at shadows of you and figure out who is who based upon your hair, your height, different physical features. But it's really not the same as seeing a three-dimensional model of you, a mannequin model of you. It's different. Okay? It's more accurate. And both be kind of creepy, wouldn't it, to have a class full of mannequins? Okay? Which would be creepier, a class full of mannequins or a class full of shadows? Okay. But which would be more accurate to lifelike? The mannequins, right? This is what we're doing. We're taking the two-dimensional Lewis structure, which is a way of representing it, but it's admittedly in two-dimensional space. And then we're going to move it forward into three-dimensional space to see what it looks like, not only with height and width, but with depth. Look at not the x and y dimensions, but also the z dimension, the z-axis. So the first one I want you to consider, this is going to be the basis on which we understand all the different geometries, is we're going to start off with the tetrahedral. Tetrahedral. So in your notes, I'd like you have tetrahedral, or the tetrahedral molecule, and I'm going to just tell you right now that the bond angles are going to be 109 degrees. You don't know what a bond angle is yet, but we'll explain that in a moment. Just write down your notes. The tetrahedral, bond angle 109 degrees. Now, if you were to look up these geometries online, you're going to find that different people teach it with different bond angles, slightly different, like less than 1. Some sources will say 109.4, some will say 109.5, some will say 109.2. Okay, we're rounding it off here for simplicity. What I want you to remember is it's 109 degrees. So tetrahedral, 109 degrees. And the way we're going to start learning about tetrahedral is go back to a familiar molecule to us, the methane molecule. You probably know it now as a CH4. Okay? This CH4 molecule, we said is in represented two-dimensional space, looks like over on the right-hand side. That's the way we typically draw it now. See, there's no, though I may drop valence electrons around the exterior atoms, there are none because hydrogen sees all of its electrons as being part of that shared bond, the shared pair that forms the bond between carbons. And we've already used this example and said, okay, this is what it looks like in two-dimensional space when I have a central atom and I have four, here's the real technical term, the four things connected to it. Okay? I've got four things. Right here it's four hydrogens. If I have a central atom and I have four things connected to it, it's going to take on a tetrahedral shape. Because if the two-dimensional Lewis structure looks the same as that, so does the three-dimensional Lewis structure. Does that make sense? I mean, if I had another molecule up here and it had silicon in the middle, SiH4, I threw the silicon in there, you'd say it's got the same two-dimensional Lewis structure. Okay, if it has the same two-dimensional Lewis structure, it's going to have the same three-dimensional Lewis structure. In other words, if the shadows are identical, the three-dimensional space is going to be identical. But right now, as we look at this, it kind of looks like a clock, right? It's flat, and we have hydrogens at the 3, 6, 9, and 12 o'clock positions. Okay, are you comfortable with this Lewis structure? Okay, you understand in two dimensions what we're looking at now. Now all I'm going to tell you is when you have this structure or anything like it, where you've got a central atom and four things connected to it, it's going to be a category, a column 4A element. Silicon, for example, in there, 4 around it. Now when we take this two-dimensional structure, Lewis structure, and bring it into 3 dimensions, it looks like this. Okay. So I want you to visualize on here that you see, don't worry about the angles right now, just see that I have a central carbon and that I'm indicating by lines that there are 4 hydrogens connected to it. Just get that part right now. You see that? That this shape, this tetrahedral shape, and see even in this source here where I got this, they said 109.5 degrees. I want you to just remember this is 109. Okay? But they took that two-dimensional shape with a central and 4 connected items, and when it translates into 3-dimensional space, it looks like this. Now, maybe right here, I'll go over here and get my model of that same tetrahedral shape this is what it looks like made out of styrofoam balls and wood dowels, okay? Now, on these wood dowels, I don't use 2 sticks to indicate a double bond. It's just there's a bond of some kind between them. And this is what I want you to see, is that if I were in 2-dimensional space, all of these would be 90 degrees apart. But when we get into 3-dimensional space, the equidistant spacing between here to here, 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 the angle between all of the sticks, if you will, all the bonds, is 109 degrees in every direction. Here to here is 109, 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 here to here is 109. They are all 109 degrees of separation. And what that represents are these electrons in this bond trying to be as far away from other bonds as possible. This, let's pretend we're looking at this bond. This bond is trying to be as far away from that bond as it can be. And the only reason it's not farther away is because when it goes farther away from this one, it gets closer to one of these. Okay? So I can't just simply push this down because I'm giving it more space here, but I'm giving it less space here. So if these were all different magnets, powerful enough to repel each other at these kind of distances, and I were to have them on strings, of course, zero gravity, right? There's a lot of different things I have to take into account. But they would repel each other to the point where they would all reach an equilibrium point that looks just like this. Because if any bond moves, while it moves away from one, it moves closer to another. And it would push harder against that other pair to go back to its neutral place. So this is a point of tension where every pair, remember VSEPR, valence, shell, electron, pair, repulsion. Right now, all of the valence electrons of the central atom are used up in all of these bonds. So the valence for this is consumed in the bonds. And the bonds are pushing away from each other. The valence shell electron pair repulsion, pushing away to form this shape. So if you were to draw it in 2 dimensions as cardinal headings 3, 6, 9, and 12, when you bring it into 3-dimensional space, it looks like this. Now what we're going to do, I should have a blank slide coming up. We're going to show it, and I'm going to draw it. This one here happens to be done in the right format that I'd like you to learn as a standard. I've had a couple up here that aren't quite standard, so what I've done is I've added a blank slide after each one so I can draw it. So I can show you the way I'd like you to present it on paper. But here's what's happening. You can see right here that I've got the central carbon, and I have 2 bonds depicted as straight lines, the standard bond like we'd use in a 2-dimensional Lewis structure, right? So when you see this, it's like, okay, there's a bond there, there's a bond here. What do these represent? Well, these are ways, a standard way in chemistry of depicting movement from out of the plane. What this is showing here, this kind of triangular looking shape, is that it's a bond just like these 2 are, but that it's coming out of the screen towards you. And the dashed line is the opposite. It's a bond just like the others, but it's going back into the screen. It's going away from you. So here's what we do. We take the structure, whatever we have, and we're going to orient it so that, in the case where there are 4 bonds, we take 2 of the bonds and we line them up in the plane of the board. So if I do this, if I take this one here and this one here and this one here and I line them up in a plane, just like the board would be, I'm depicting one pair that are attached to this hydrogen as coming out toward you. And that's what I depict here. It's coming out toward you. And I have one pair over here that's connected to this hydrogen, which is behind it, which is going away from you. And I show that by the dotted line here, that it's going away from you. You see that? Okay. So if I were to create that VSEPR diagram, the 3-dimensional Lewis, so with the VSEPR of this molecule here, again, it would be a central carbon with 2 hydrogens. Right now, these 3 are in a plane. They're in the same plane as the board. They're in the plane of the board. I have 2 more that I need to draw. This one I draw down with a triangle, long triangle, and that's showing that I have a hydrogen that's in this general area and it's coming out toward you. I'm going to draw a second one back like that, which shows that that hydrogen is actually behind the plane of these three. So this hydrogen, because of that triangle, is forward. This hydrogen, because of that dot, is behind. And that's how we represent the tetrahedral. All right? 109-degree bond angle. What does that mean? That means where there are bonds, the angle between them is 109 degrees. Because we're going to very quickly move right now to the next shape, the next geometry, and it's not going to have three. No. It's one of the dangers of allowing these things to be distributed. Those kind of things can happen. Like, people go, oh, this is fun, and pretty soon it can't stick anymore. So, everybody comfortable with the three-dimensional tetrahedral? Okay. Then let me erase this. And we're going to move on to the pyramidal. The pyramidal, bond angle of 107 degrees. While you write that, let me go over here and get one. Okay. Pyramidal of 107 degrees. A good example of a pyramidal is ammonia. Okay. Ammonia, when the molecules form this Lewis structure, we have a nitrogen, which is a category 5A element, forms single bonds with hydrogens. So the nitrogen and all the hydrogens, their valences are satisfied, and that's how we represent this shape in 2 dimensions. Okay? Again, you should be comfortable with this by now. Okay. But what's different about this than the CH4 molecule? 3 bonds and an unbonded pair. See that? There's a pair up here, and then pairs, but they're in bond form. Okay. Now remember that what we're talking about is VSEPR, the valence shell electron pair repulsion. The reason why this has a bond angle of only 107 degrees in 3 dimensions is because of the effect of a unbonded pair as opposed to a bonded pair. And the principle is this, that the unbonded pair push away stronger than a bond. Okay? Maybe you can think of it this way. This pair of electrons here, sometimes this electron is closer to nitrogen, but sometimes it's closer to hydrogen, right? This pair, guess what? They're always right next to nitrogen. They're closer and pushing harder all the time, pushing away from. So, what does this then look like in a 3-dimensional space? This, like I said, this is a pyramidal, sometimes referred to as a trigonal pyramidal. Okay? Because later on we're going to do a trigonal planar, and it gets confusing sometimes. So just remember this one is the pyramidal. If you want to get technical, it's a trigonal pyramidal. Bond angles of 107 degrees. In 3-dimensional space, it looks like this. Now, the solid and dotted lines are different. I'm going to draw it again in the standard way I want you to draw it in just a moment. So don't copy this right now, but I want you to visualize it, look at it. All right? If we had 4 bonds, remember, it would look like a tetrahedron. But we don't have. What we've done is we've put what's called the unbonded pair on the top, and we've already said that the unbonded pair pushes away more than a bond does, right? Now, this 109 degrees represents when all of these forces that are pushing away are all equal. And this is the equilibrium point. This is the geometry that corresponds to that equilibrium. If I were to take this pair off and put something there that pushes away harder than bonds, what would you expect these 3 atoms to do? If I increase the repulsion from the top, what would happen? Don't know? Okay, again, if here there's 4 bonds and they repel equally to this place, if I take this off and I put something on here which pushes harder than these push, can you see that it's going to take those legs and squeeze them down? Okay. Now, for a lot of you, they had no clue as soon as I said, they were like, oh yeah, I get it. Okay. Do you? If I put something here that pushes down harder than what was there before, then this shape gets modified by these three things. Again, it gets pushed away from it and closer together. And that's where those 2 degrees of difference come from, between 109 and 107. Is because I'm about to replace this bond that was on the top. I'm going to replace it with the unbonded pair. This unbonded pair pushes away from these bonds stronger than a bond would, which means when they were 109 degrees apart, now they're getting squeezed down and it's 107. So in 3-dimensional space, what I'm going to do is draw my nitrogen, my central atom, and I'm going to start by placing unbonded pairs at the 12 o'clock position. Okay. This is what I want you to draw, but I want you to visualize now that if this were a bond, that I would have a hydrogen here, and I would have a hydrogen here, and I would have a hydrogen here. You see that? Okay. So basically, in terms of 2 degrees, freehanding it, not a big difference, right? If, and this isn't a correct geometry, but if that were an actual molecule, this would be a tetrahedral. But since it's not, it's now a pyramidal. Because there is no structure to the north, using cardinal heading, right? There's no structure up here. There's an unbonded pair, and it's taken the legs and squeezed them together. And sometimes I'll just refer to this as the tripod. The trigonal, or excuse me, the pyramidal here, this trigonal pyramidal. This pyramidal is a tripod, and I will occasionally in class point over to the tripod that holds our camera and say, what is the geometry of this molecule? Hint, boom, it's a pyramidal. If you look at the camera right now, consider the camera to be the nucleus, and it has 3 legs. But the camera, little flip top on it, that's the unbonded pair. And that unbonded pair is pushing away harder than the bonds push away from each other. And so it's forcing the legs to get squeezed down at the bottom. Okay? Now that's a gross exaggeration, but that's the concept. So this Lewis structure with 4 connecting points to the central, but one of those connecting points being filled by an unbonded pair, okay, creates not a tetrahedral, but a pyramidal with a bond angle of 107 degrees. Where does that bond angle of 107 degrees exist? It exists between these lines. Every way you look between one hydrogen and another, it's all 107 degrees in all directions, okay? Now the closest direction, not all the way around, of course. But the closest line between the two is always going to form an angle of 107 degrees, which means that this angle here is greater than 107 degrees, right? It's actually greater than 109 degrees because it was 109 degrees as a tetrahedral, and now it's pushing them even farther away. But you don't need to worry about what that angle is. The bond angle of 107 degrees is the angle between these bonds in all directions. All right? So, we're basing off the tetrahedral, 109 degrees in all directions. We modify the tetrahedral by replacing one bond with an unbonded pair, and that squeezes the legs in and converts us from a tetrahedral to a pyramidal, or more precisely, a trigonal pyramidal, of a bond angle of 107. Why? Because the unbonded pair is pushing away, is repelling the other pairs stronger than a bond would. Yes, sir?
So the 107 is just between the hydrogens?
Yes. With the nitrogen at the vortex, okay, that's your angle. So it's from the nitrogen. This angle here is 107. This angle here is 107. This angle back there is 107. In all directions, it's 107. Between it and the unbonded pair, not 107. But you're not going to be asked that. I just want you to understand what the 107 stands for. In the tetrahedral, it's 109 in all directions because all we have are bonds. Okay. So, the pyramidal. So what are we going to do next, do you think? We have a central atom with 4 connecting points. We said we started with 4 connections all being bonds, forming a tetrahedral. We took off one leg, put it an unbonded pair in there, and now we have a pyramidal. Still 4 connectings, right? 3 of them being bonds and 1 being an unbonded pair. The next progression in the evolution is 2 bonds and 2 unbonded pairs. Very good. It's the bent molecule of 105 degrees. Do you see a pattern there in the degrees? We go from 4 bonds is 109, 3 bonds is 107, 2 bonds is 105. Each one is off by 2. Okay? Just a hint there in case you didn't pick up on that. Because that's 4th grade math when we get into, never mind. Okay, so, actually it's not. It's actually closer to 1st grade math too, but 105 degrees. What does that look like? Well, we'll use an example here of water. The Mickey Mouse molecule. I'll be very familiar with Mickey Mouse here. And see the way we're depicting this. We have a central atom. It has 4 potential points of connection, 2 of which are bonds and 2 of which are unbonded pairs. And in our geometries, we're always going to put the unbonded pairs close to each other and the bonds close to each other because that's the way it plays out. That's the way how it affects the geometry in 3 dimensions. So is everybody comfortable with a 2-dimensional H2O? All right. 3-dimensional. It's got 2 unbonded pairs and 2 bonds with hydrogen. Again, here it says 104.5. We're just learning 105. Okay. How does this look as I draw it out? Well, let me first go get my model. I have a central atom with 2 bonds and 2 unbonded pairs. Okay? Central, 2 bonds, 2 unbonded. The way I'm going to draw that in 3-dimensional space, we're always going to put the unbonded pairs in the plane of the central atom. So if I take this and I put it so that both of those unbonded pairs are in the plane of the atom, see that? Or in the plane right here of the molecule is what I should have said. In the plane of the molecule right here, if I put those in the plane, that means I've got one coming forward and one going back. I draw that using water as an example. I have a central atom. I have an unbonded pair, an unbonded pair, just slightly greater than 90 degrees apart, and then my 2 points of bonding connection. Okay. The angle between these bonds, this bond right here, there's only one angle to measure, is 105 degrees. Why? Well, it would have been 109 with 4 connections, 4 bonds. It would have been 107 with 3 bonds and 1 unbonded pair. So now it's 105 with 2 bonds and 2 unbonded pair. And the point to remember on all 3 that I've shown you so far is that this is based upon a central atom with 4 points of connection. When you draw your 2-dimensional Lewis structure, that you have 4 points of connection around that central atom. Okay. Now there's going to be times when there aren't 4 points of connection. We're going to learn 2 of those geometries next. But these 3 are based upon 4 points of connection to the central atom. Those points of connection really are these bonds, and this could be a bond, but since it's not bonded with anything, it's an unbonded pair. Okay? 1, 2, 3, 4. 4 points. Draw the 2-dimensional Lewis structure, you would have 1, 2, 3, 4 places around the central atom. The pyramidal, same idea. 4 points, potential points of connection. 3 of those are bonds and 1 unbonded pair. And the tetrahedral, 4 potential points of connection and 4 bonds. Okay? So when you learn these 3 geometries, learn the tetrahedral and consider each of these a modification of the tetrahedral. You ask yourself, okay, how many potential points of connection do I have on the central atom? 4. The shape is going to be some modification of a tetrahedral. Are those 4 connection points full with bonds? Yes, it is a tetrahedral. Are all 4 points connected with bonds? No, one of them is an unbonded pair. It is a pyramidal. Does it have 4 points of connection? Yes, it's some modification of a tetrahedral. How many bonds does it have? 2. 2 bonds, 2 unpaired, 2 unbonded pairs. It's a bent molecule, 105 degrees. Okay, so it's that kind of question every time. How many points? 4. It's a modification of a tetrahedral in some way. It's going to be a tetrahedral, a pyramidal, or a bent with 107, or excuse me, 109, 107, or 105. Okay? So you can see where the key is being able to draw a good 2-dimensional Lewis and then say, okay, that 2-dimensional Lewis translates into this 3-dimensional VSEPR diagram. We have 2 more shapes we need to learn. Let me go ahead and erase this first so it's not noise under the slide. The trigonal molecule. Now, as I said before, the pyramidal is technically a trigonal pyramidal. We just simplify that to be pyramidal because this molecule is just a trigonal, or sometimes called a trigonal planar. But to simplify it, if you just learn this one as the trigonal and the other one as the pyramidal, we're good. If you want to know why it's got a double name, there's a very logical reason for it, but it could get confusing. And I will apologize in advance. If I refer to something as a trigonal pyramidal, I'm talking about the pyramidal. If I talk about a trigonal planar, I'm talking about the trigonal. Okay? Again, words you're not used to hearing, but by next week it'll be so common you're like, yeah, that's as simple as electron configurations. All right, so the trigonal molecule. And we're going to use the example of 3 different examples. I pulled this picture of formaldehyde, sulfur trioxide, and phosgene. Okay? When you do the 2-dimensional Lewis structures for every one of these, you're going to find out that they have at least 1 double bond. The result of that means that there's only, how many points of connection are there around the central atom then? There's only 3. If there's a bond or a double bond or a triple bond, and in VSEPR, they consider each one of them to be equal. They are different, but the differences are so minor that for our purposes, we're going to consider them to be of equal force. A double bond is not stronger than a single bond, is not stronger than a triple bond in terms of how they repel each other. They are stronger in terms of what kind of energy it takes to break the bond. We've discussed that. Okay, from the gamma rays to the X-rays to ultraviolet rays. We're not talking about the strength of the bond. We're talking about is how do they repel one another. And so a single, double, or triple, they all repel in the same way. And frankly, you're only going to have to deal with singles and doubles. Because once you get to a triple, guess what? There's nowhere else for anything else to really join, right? And it becomes a linear. And we'll talk about that in just a moment. So this is a 2-dimensional structure for these different molecules. And let's just consider the center one here. Actually, this one's probably more familiar to us, more obvious. You've got carbon, which would have 4 connecting points. The chlorines are both wanting to share 1 electron, so they form that bond. The singles, and then oxygen wants 2, and carbon has 2, so they work out the double bond. 2-dimensional Lewis structure, carbon with 3 molecules on the outside. You ask yourself a question after you draw the 2-dimensional Lewis structure, how many points of connection do I have around the central atom? And you look at that and you say 3, not 4. If I had 4, it's some modification of a tetrahedral. But I don't have 4, I only have 3. And as I started to allude to at the end of the last module, they're going to start repelling each other equidistant apart, right? They're going to start pushing away from each other so that the spacing, the gapping between them is exactly the same. Well, here's the beauty of the trigonal, is that a trigonal model is the same as the Lewis. Because look at this. Every one of these bonds is the same distance apart, and they form a plane where they're all 120 degrees here, but they all reside in the same plane. Because if anybody moves up this way, these guys are going to push away and go that way. It always stays. This is the equilibrium point of a trigonal. When I have 3 points of connection around a central atom, they're going to be 120 degrees apart, but nothing comes in or out of the plane. They're all in plane, which means there's no triangles to show something coming out, and there's no dashes showing something going back. A trigonal molecule is in the plane. And that's why, although I said I wouldn't tell you all this, that's why it's called a planar, a trigonal planar, because it's all in the plane. 3 points, like a triangle, trigonal, but it's in a plane. That's why the pyramidal is technically a trigonal pyramidal, because there's 3 points, trigonal, but it's set up like a pyramid. Okay? So here, the trigonal, with 3 points of connection, it will lay out with the bond angle of 120 degrees. And again, that's whether it's a single, a double, whatever. Every bonding set are separated by 120 degrees in the plane. Okay? So we don't need to draw anything else other than the two-dimensional to show the three-dimensional for our trigonal. Again, the key here is that there are 3 points of connection around the central atom. If there were 4, it would be a modification of a tetrahedral. Either a tetrahedral, a pyramidal, or a bent. If there are 3 points of connection, it's going to be a planar. Planar trigonal. Trigonal planar. Okay, sorry. See, I'm doing it already. This is a trigonal. This is what I want you to remember it as a trigonal. A trigonal planar is what it is. So, okay, one more geometry. Linear. The linear molecule has a bond angle of 180 degrees. How do we get a linear? Well, there are 2 ways that we can get linears. One is that we have a central atom with only 2 things connected to it and only 2 connection points. When I draw, for example, the CO2 molecule, and I look at carbon, it has 4 valence electrons. It's looking to share 4. And I have oxygens, 2 of them, each looking to share 2. They form this relationship where I have a central atom and 2 atoms bonded to it. And guess what? These 2 are pushing against each other. Can you see that if this one were to come closer here, this one would be compelled to move away? And if this one came down here, this one would be compelled to move there? Because the distance from here to here has to be the same as the distance from here to here. And it forces it to be in a straight line. The forces that are repelling these pairs and these pairs are pushing away at equal strengths. And so if anything were to come along to bend it down, this side would, by equalization of forces, have to go up. If the distance here is greater or less than the distance here, it will automatically modify itself to go back into a straight line. Okay? And what does this look like in 3 dimensions? Well, here's another beauty. It's a 2-dimensional structure in the sense that it stays in a straight line. There are no dotted lines coming in and out. Everything's in a straight line. It's in a plane. Okay? So, when you have a central atom with 2 connection points, both with bonds, boom, it's a linear molecule. Bond angle of 180 degrees. There's one other way that we can have a linear. What do you think that is? Go ahead. Did you have a? Well, not. This orientation is in all directions. So it's not the fact that it's left and right. It's just, it shows you that if any time you came to one end and looked straight across, they would all be in a straight line. There is no depth. We're considering, again, if I were holding like this and I turned it like this, but if I came over here and looked down the end, it would still be a straight line. So it's its spin, its orientation, that doesn't affect it. Okay. Homonuclear diatomics. See, up until now, we've had a central atom, a pivot atom, and the angles between them. But if we only have 2 atoms connected to one another, it's always linear. Because there is no pivot point. There is no central atom from which the angle can vary. I just have 2 things bonded to one another. See, I basically have no central atom. I only have 2 exterior atoms. And they are always going to form a linear. Again, if I were to, whatever the perspective is, orientation in space, if I bring myself to look at the end of one of them, it'll always be in a straight line. And there's no way that this can pivot, right? You have to bend the angle. You have to bend the bond, because there's nothing for it to bend around other than the bond. So your linear molecules are either not just homonuclear diatomics, that's a good example of it, but two atoms bonded to each other is going to be linear. In order for it to be something other than linear, it has to have three or more. Then it could potentially be. But if it has three, it's going to look like this, right? If the central atom can hold, if the central atom only has two connection points, and there are three atoms in the molecule, it's going to be straight. Or anytime there's two atoms in the entire molecule, it's going to be a straight molecule. Now there's another kind of bent molecule that we didn't get into. You don't need to have it for your notes, but it does exist, where you have a central atom that has three connection points, but only two bonds to external elements. I just show this to you because it kind of fits in the mix, but don't worry about this shape right now. It's another kind of bent molecule. So, with about 3 minutes left, right now, any basic questions about VSEPR? Because these are the geometries. You've seen every geometry you're going to have to know. And hopefully now you know that if you can draw it in two-dimensional space, and remember, hey, that two-dimensional space looks like this, or this model in two-dimensional space looks like this in three-dimensional space. And just draw it. Placing two of however many points there are, and again, we're talking about coming forward and going back only in the case of modifications of the tetrahedral. So in a tetrahedral, when I draw this one, I put two bonded atoms in plane with the central atom. One comes forward and one goes back. When I only have three bonds and not four bonds, I draw it by placing the unbonded pair and one of my bonded elements in the plane, which means I have two, one coming forward and one going back. When I have two unbonded pairs, I draw it by placing both of the unbonded pairs in the plane, and then I have one coming forward and one going back. Once you only have three connecting points, it's a trigonal planar. It's a trigonal in the plane. And when I have two, it's always going to be linear, straight line. So again, you only need to worry about drawing elements coming in or out when you're doing a modification of a tetrahedral. I didn't plan very well. We've got, what, a minute? So, no questions right now. I know there'll probably be some tomorrow. So go ahead. Next we would go through the examples and look at things like this. Let's take our minute and think about this one. What's the shape and bond angle of a PHCl2 molecule? What is going to be my central atom? In my Lewis structure, it becomes my pivot atom in my three-dimensional molecule. Well, there's no carbon in this molecule, so.
Phosphorus.
Okay, phosphorus, right? How many does, what column is phosphorus in? Column 5. So I know that I'm going to have a phosphorus right here. In 2 dimensions, I would draw it like this, right? I'd probably have a hydrogen here, and a chlorine here, and a chlorine here. Are we good with that? Okay, what is that shape in 3 dimensions? What's it a modification of? Tetrahedral. How do we know? 1, 2, 3, 4. There's 4 connecting places. It's a modification of tetrahedral. Is it a tetrahedral? No, because it doesn't have 4 bonds. It only has 3. So it's a pyramidal. Pyramidal, because these are going to push these away, push them away, and it's going to result in